different topics, and we are going to start with the first one, which is miniaturized 3D microscope and reflectometer for space exploration. It's by Gustav Peterson, Michael Dilley, Sarah Abramson, Ulan Wong from KTH Royal Institute of Technology, Intelligent Robotics Group, NASA MS, and University of California, Santa Cruz. Gustav Peterson is going to present it for us. Go ahead.
Do you hear me in the back? No? All right, I will hold it. Is this better? All right, fantastic. So there is a planet. On this planet, there is a gift you really want to open. We are here on Earth. You have built some instrument for looking at this gift, and of course, what you do is you go to the planet and you look at your thing, and everyone's happy. So you propose this to NASA, and then they say, "Oh, sorry, I can't do that. It's a bit expensive." So we do the second best thing, which is that we take our instrument and we put it on top of a car, and we send the car to the planet. Us, the scientists, we remain on Earth, and you've built yourself a Mars rover, right? Fantastic. So the pinnacle of space exploration is, of course, the Curiosity rover, right? Which is basically a fully featured chemistry lab on Mars, right? One thing that I think not everyone understands is just quite how big these things are, right? So the Curiosity rover weighs almost 1,000 kilograms, and it's the size of all of these tiny Japanese cars you see driving around. It has 9 really, really excellent chemistry instruments, and it also has a bunch of tools to do the human's job, right? So it has a drill for getting samples, it has a scoop for getting samples, it has a laser to vaporize rocks to do spectrometry. Really cool things. So it's definitely the coolest robot in the solar system. And if you want to go see the second coolest robot in the solar system, you can go to JPL, NASA JPL, where they have Maggie, which is Curiosity's sister rover, which is basically identical but here on Earth. There is, however, a problem with doing exploration with these rovers, right? So they're really big, they are really expensive. So what is going to happen is that we're going to need to replace these rovers, because there are a bunch of places where we want to go where we don't dare to take our rover just because of the risk of losing it, or where we can't go to the rover because it just doesn't have the capability of going to certain places. So therefore, these big rovers are going to be replaced by some smaller, more versatile explorers that can go to different places. Right, and so the purpose of this would be to go where we can't go right now. So we have, for example, a bunch of craters, which are really interesting, right? Because these are high energy impact, so you want to see what's going on in the craters. You have mountains and you have rivers, river banks, which we can't go into. And one feature which is very prominent on Mars is lava tubes. So this is lava flow under the surface of Mars, which leaves this really long cave, right? So tens of kilometers long caves, and you see them as these streaks where the roof has collapsed. So they're quite extraordinary, and you would want to go inside, right? What is inside we don't know because we can't go there. Yes. So these new explorers are going to be different. One specific project in doing these new exploration things is called SPEARS, which is the project that this work is a part of, which is it's a bridging the gap concept. So we want to take the benefits of these big rover missions, which we have a lot of experience with, and we want to add some of what we call extreme exploration capability. So going to places where we can't go, we call extreme exploration. The way we do that is we take our rover, and on it we mount a pneumatic cannon, right? So in here, you put something, which is actually your instrument, which you then launch out of the rover into wherever you want to measure. So where you can't take a rover, you just shoot your instrument, and then you do your measurements. Problem with this is that the instruments need to change, right? So the old instruments we have, they're really big, they're really complicated, they're fantastic, but we have huge new constraints if you want to do a different kind of exploration. So the biggest one is that they just need to become smaller and use less resources in general by usually a couple of orders of magnitude. So it's a complete step change. They will have to use a lot less finesse. So you have a less complicated platform. It's very much you take your instrument and you plunk it down somewhere and it just needs to do its thing. And they also need a lot less platform specialization. So if you want to be able to put the same instrument on different platforms, or you want to use different platforms with one instrument, then you can't rely on platform constraints. Like you can't say that, oh, we need to have a scoop, because if you're on an exploration platform which doesn't have a scoop, you can't do anything. So the question then is can we use computation to augment these new instruments which are constrained to bring back some of the interesting things? So our solution is to recreate the visual having a sample in the lab experience with computational photography. So we start with an image of, and I apologize for the quality of this projector, a microscopy image. So if you look at this with your eyes or in a normal photograph, it just looks like sand. It's brown sand. But if you zoom in enough to see this on the grain of sand resolution, you see a lot of really interesting features, and I'm not qualified to talk about them. But these features, they tell the story of the sample. But we don't just want a normal photograph like this. We want to be able to give the scientists the opportunity to look at this in whatever direction they want, and with any illumination they want, to understand more about the sample. And we do this, as I will show you, with some computational photography things. Excuse me. Another thing we want to do, which I want to talk about today, is to measure some physical properties of these. And then why I'm here is to get you guys interested, right? What else can we do with computation? So what we did is basically a three-stage process. So we created some physical devices. We put together a simple 3D reconstruction system, and we did some experimental validation of our results, because we really need to show that this works. So you see, we built two hardware prototypes. So in each of these, you have, if you start from the top, a camera sensor. Then there is a lens. In front of the lens is a coded aperture. So it's an LCD, which we use as the aperture. Then you have your second lens, which is for focusing the light from the sample. And around the sample, there is this hemispherical shape, which is the illumination that we put on the sample. So the miniature version here on the side, it fits in these new constraints that we need, which is really, really important, because we could actually potentially put this on one of these new exploration systems where today we basically have nothing, right? So there are a bunch of ideas for how you build your exploration platform, but no ideas for what we're going to put on them. So the principle, it's a simple programmable aperture. So you have some objects on the left-hand side there in the focal plane. If you move the aperture in a system, you get a parallax effect. So the objects which are not in the focal plane, they appear to shift. And with that, you can get the 3D structure. The second thing that we do is with the illumination, is that we have illumination from different directions, and then when you shine a light from a certain direction, you get different shadow patterns, right? So I just want to start with showing what the raw data looks like. So if you take just the aperture and you move it in a circle, you get this perspective shift, and you can already see, right, with your brain that this is you can see the 3D structure. You can really appreciate it. And you can also see how vastly different these different samples look like. Whereas in the sort of the normal scale, they all just look like sand, right? And then the same for the illumination. Sorry, I'll just give you that for a second more. Where you can see how when you illuminate from different sides, you get different shadows. So for reconstructing this, we do very boring methods by your standards. We do a simple multi-view stereo on the aperture data and a photometric stereo on the illumination data. And we do a per pixel quality scoring in both of these data sets, because what we want to do is then fuse them together into a single height map. And we do this by minimizing a cost function, which is basically you take the Q here is the quality of your measurement. And then you have either Z, which is the direct height measurement from multi-view stereo, or S, which is the slope measurement from photometric stereo. And you optimize this, and I think you can all see that this is easy to rewrite into a matrix equation. It becomes a sparse matrix equation, so it's very easy and fast to solve. One reason why this is so good for us is because multi-view stereo and photometric stereo are extremely complementary forms of 3D reconstruction. So if you have something with a lot of texture and you need a global measurement of how far away it is, multi-view stereo will give you a really good measurement of how far away something is. If you have something which doesn't have any texture, your multi-view stereo isn't going to do anything, you're going to get, excuse me again, really good results with your photometric stereo, because you don't have any texture that sort of ruins that, but it's a local measurement. So if we can take the benefits of each of these, then we can reconstruct many more different samples, and that's important for us because we don't know exactly what we will be looking at, right? We need to be able to test a wide range of things. So as an example here, I'll tell you what this is later. If we image something which has not so much texture and it has this three-dimensional shape, we do our multi-view stereo. You will see on the features in this, we have good absolute values of how far away they are. In the flat regions, we have a lot of noise. If we look at the photometric stereo, in the regions where we have a lot of noise up here, we don't have we have a really nice value from the photometric stereo. The problem with this, of course, is this doesn't actually give you the 3 dimensions. Right? This gives you the normal vector, so the angles, and you need to somehow integrate this to get the 3D shape. And since we have discontinuities, it's impossible to actually determine. So if we look at these quality scores that we made, the ratios of the quality directly tells you this let's say the same as your intuition of where it works very well, and you can fuse them to get a height map which keeps the global information from multi-view stereo, but the nice smooth shapes from photometric stereo. So we're very happy with this. Well, what we do is we really we need to show some quantifiable results. So in a lot of what you do here, you show a cool demo, everyone's happy. When we go and we propose this to the scientists, they want to know exactly how good something is and when it works and when it doesn't work. So we had to create a fiducial for measuring this. And so making a fiducial for a microscope is hard because we look at really small things, but we created this object, which you saw in the previous slide, and it's really small, right? So this is a penny, so it's smaller than Abraham Lincoln's nose on a penny. And you saw the first talk this morning. There was a brief mention of a lithographic 3D printer, and we actually use exactly the same thing. It's called a nanoscribe. So to make one of these, we print out this fiducial on a nanoscribe. We cover it in silver, and then we corrode the silver to give us a texture more similar to a natural material. And so this is the nanoscribe on the left, and this is me corroding things on the right. So there's a mixture of very, very clean and not so clean. But so when we measure this, we can take the texture that we get from the 2D image, and the height map, and we can see that we get really, really good reconstruction results, right? And you saw that the photometric stereo and the multi-view stereo separately aren't very good, but together they're really nice. And since we created the fiducial, we can also say exactly what the error is when we do this. So we can go to the scientists and we can say this is exactly what you can expect in your results. So we find typically that the error is around 5 micron in the vertical axis. And it depends. So the first 3 columns here are for the 3 different features in the fiducial. And then the last column is if you take the entire fiducial and you look at the error over the whole thing. And what you notice in this is that there's a lot of error in where you have discontinuities, and this is kind of expected and kind of okay. But for the actual features we care about, they're about 5 micron. And what's really interesting here, is that we get about pretty similar results to if you take your thing, you put it into a normal commercial microscope you find in a lab, you do a C-stack, which we've heard about earlier, and you do just shape from focus. So these are the results for the fiducial, and then we have imaged a bunch of different regolith simulants. So this you've seen before, the Mars. You can see an asteroid looks completely different, right? So new exploration in space, it really drives new instrumentation. We want to use computational methods to add value to our data without adding mass to our measurement device. We designed this system which we presented, and we also created this 3D resolution calibration target to actually verify that this thing works. So I mentioned briefly that we want to do BRDF modeling. So we have a 3D reconstruction, and we have a very determined system geometry where we decide the direction that we look from with the aperture and the direction that we illuminate from with the LEDs. And therefore, we can have both the incident and the exit angle of your light at every point in the sample, and therefore we can measure the BRDF, which has physical meaning. So this is a big thing that we want to do in the future. We're really happy with the fiducial, but we think we can do more, in particular adding microtexture to it. So it's a bit smoother than the natural materials. We could potentially do better there. And then why we're here, of course, is all of your ideas. So what we can give you is complete control of the aperture and the illumination of a microscope on Mars. And I come here as a non-computational photographer, and I ask you, what should we do with this? What are the really cool things we can do? So there are a bunch of people that made this happen. I just want to put up this slide to thank them. And then I also want to thank you for listening.
Great work, Gustav. Nice to see that computational photography will one day go to Mars. We have time for a couple of questions.
Hi, thanks. Great talk. I'm curious why do you need the 3D information? Like, what is it actually telling you about the sand that is useful for an actual scientist? Because I think oftentimes I'm a little detached from what real science cares about.
Right. So there are different aspects of the 3D information. One of them is the thing I mentioned about the physical modeling, like the BRDF modeling. If we have a shape of the sample, we can do an interpretation of the scene, right, where we know the geometry, we know the occlusion, so that we can actually do really potentially really good BRDF reconstruction. And when we do this, they have a physical meaning, right? There's an interpretation to the BRDF. The other thing is that let's say it's a more simplistic part of it is just the shape of each of these grains of sand that we're looking at. So the particle size distribution actually tells you a lot about the history of the site that you're looking at. So if you take, for example, a riverbank, right, depending on the energy of the water flow, and so if there are any scientists in here, I apologize if what I'm saying is wrong, but this is my understanding. The energy of the water flow, right, it selectively filters out the size of the particles, right? So if you imagine you take one of these helicopters and you put one of our microscopes under, and you follow along in a riverbank, and you take measurements. You can see, you know, how did the water flow evolve in this, for example.
Yeah, I think maybe we can take one very small, quick question. We have like 30 seconds. If not,
So, quick question: how much time does it take to reconstruct everything? Like, how much time does it take to get a 3D and everything with the sample?
Yeah, so a long time is the answer. Not a super long time. So we are actually. Do you want this? What we're doing is really not time constrained so much as in many other things, right? Because we'll be looking at only static things, and we will be so. If we find something which is not static on a planet, that would be a Nobel Prize. So the scene is static. So how long it takes to actually capture an image doesn't matter so much, but takes, you know, an order of a minute or two, because we have actually a lot of images that we need to capture. And the reconstruction, it's not been optimized to be any fast, but it takes like 20 minutes to do or something. So it's
thank you, Gustav, again. We can thank him again.